This is Professor Darif Seitz. Central Limit Theorem. This video shows how to use Microsoft Excel to do calculations related to the Central Limit Theorem. The Central Limit Theorem is about sampling distributions of a sample statistic, in this case, X bar, the mean of a sample. The idea is that you repeatedly take samples of size n from an underlying population, the population for X, and for each sample you calculate the mean of the sample X bar. And those set of X bars form their own distribution, which is called a sampling distribution. And the Central Limit Theorem makes significant statements about the sampling distribution. In the left-hand side of this spreadsheet, you need to enter some data that it will use in order to do the calculations. Starting with the second row, we'll go back to the other one in a minute. Mu is the X population mean, the underlying population, and sigma is its underlying standard deviation. N is the sample size for each sample. And in order for the sampling distribution to be close to normal, then the underlying population must be normal, or the sample size must be greater than or equal to 30. Up here, you can put a particular value for X bar that will be used in the lower part down here. The first thing in the lower part, coming from the Central Limit Theorem, is that the mean for the sampling distribution, the mean for X bar, will be equal to the mean for the X population distribution, mu. It's equal to mu. Next, the Central Limit Theorem states that the standard deviation for this sampling distribution, sigma X bar, will be equal to the standard deviation of the population divided by the square root of n. So we see here for this case, 3.8 for the population standard deviation, and down here, since it's been divided by the square root of 50, it's smaller. This sampling distributions has a smaller standard deviation than the population that it's based on. The last row down here will calculate a z-score for this value of X bar given the statistics for the sampling distribution. Look at the formula here. The z-score is B1, which is the X bar value that you're interested in generating a z-score for, minus B6, which is the mean for the X bar sampling distribution, and divide that by B7, the standard deviation of the sampling distribution. On the right are some very convenient calculations. You can put in a value for X bar 1 and X bar 2, and using the normal distribution for the sampling distribution, as we'll see here, it will give you the probabilities of being in the interval less than X bar 1, to the left of X bar 1, which is the area under that curve, probability of that interval to the left of X bar 1, or the probability to the right of X bar 2, or it will also give you the probability of being between X bar 1 and X bar 2. look at these formulas. This first one here, less than x bar 1, uses the normal distribution. F1 is x bar 1, 11 in this case. B6 and B7 are the mu and sigma for the sampling distribution. And true means use cumulative area to the left. The next one below it, area to the right of x2, you get that by doing 1 minus the area to the left of the x bar 2 value. So that's why we have F2 up here for the x bar 2 value, B6 and B7 for the mu and sigma and true, and this last one to get the interval in between x bar 1 and x bar 2, you take the larger one to the left of it, subtract the smaller one to the left of it, and you will get that probability or area under the curve. This spreadsheet is versatile. You can use it to get your basic sampling distribution information over here, and for more typical advanced inquiries about probabilities in the right-hand side. And I should point out that this statement here about x bar being less than or equal to x bar 1, this x bar is just talking about values in general from the x bar sampling distribution. Don't interpret this x bar here to be the same as 11, this x bar there. These are two different contexts, the left-hand side and the right-hand side.